Okay, so let's move on to talking about what to do when your factors are not distinct. So we already reviewed what to do when your factors are distinct, like this. Quadratics go in the denominator and get an unknown linear in the numerator. Linear factors go in the denominator and get an unknown constant in the numerator, okay? So we're going to move on and now discuss what happens when the q of x here has a repeated factor. Okay, so let's imagine that q of x has a linear factor that's aligned like an mx plus b. In this case, I'm writing it as ax plus b. And it's repeated r times. Repeated means it would appear with a power in the factorization of q. Okay, so normally what would happen if you just had a single power is we would have just a single partial fraction. But now what happens, since it's repeated r times, repeated r times goes with r partial fractions contributed. To the decomposition. So remember, the decomposition is what I would call the entire right-hand side here, and the individual terms would be the partial fractions. And I'm now saying that if you have a linear factor that's repeated r times, then you actually need to make r different partial fractions in this list here, okay? And the partial fractions all differ in the denominator, where the power is counting up to r. So you have an unknown constant over the linear. This much would be identical with what we would do up in the original case, okay, like this e over x plus 1. But now we have to count up the powers. Now we get another partial fraction like this, another one like this, and like this, okay? So for example, for this rational function here, I have an unknown, an irreducible quadratic. So it goes over here and we have an unknown linear. Over here, we have a linear term, a linear factor, and so we have an unknown constant. And then we have this linear term, which is not distinct. It's been repeated 3 times. And so we have to list it out, 1, 2, and 3, okay? So this guy right here goes with all of those 3 things being contributed to the partial fraction decomposition, okay? The same rule applies for irreducible quadratics that are repeated, so it's very easy to know what to do there as well. So again, a quadratic looks like this, and if it's repeated r times, then it has a r power here, okay? So let's get another color here to underline these guys. Repeated r times, and like this guy right here. And what you get to the contribution is this. R partial fractions contributed to the decomposition. Okay, and the partial fractions are all of the exact same form that we just learned for linear. Basically, you start off with sort of the normal one, this one over here, just like in our example above. Here's a quadratic that wasn't repeated, so it just got a single guy. So that would just be like this. Here's a quadratic, and then a single unknown linear in the numerator. But now, since this one was repeated r times, it's got a factor, an rth power here on its factor, then you're going to count up. So there's the second partial fraction contributed, still has an unknown linear in the numerator. The third partial fraction contributed still has an unknown linear in the numerator. And you just count all the way up to r for a total of r partial fractions contributed to the full decomposition. Okay, so if we want to do for this guy, this example, then we've got this quadratic, which is irreducible and repeated twice. We've got this quadratic, which is irreducible but not repeated, or you could even say it's repeated once. I guess a better word in that case is multiplicity. Its multiplicity is 1. Here we have a linear, its multiplicity is 2, or it's repeated twice. And this one over here, a linear repeated just once, or distinct. Okay, so this one is ready to go for a partial fraction decomposition. So I'm just going to write it out. I should probably do it on the next line because it's going to be kind of long. Because how many fractions are we going to have? How many partial fractions are we going to have? We're going to have 1, 2, 3, 4, 5, 6. So I'm going to have a list of 6 different partial fractions contributed here because of the repeats. Okay. So here I'm going to have x squared plus 1 with an unknown linear. And then I'm going to have x squared plus 1 again, but now to the second power because it's repeated twice in my factorization. And I need another unknown linear. So cx plus d will do. Moving on to the next, I have irreducible quadratic that's distinct. So it just has a single partial fraction, and I need another unknown linear. So ex plus f, say. And now we're moving on to this guy. This is a linear which is repeated twice. So I need 1 partial fraction, which is like normal, the linear factor with an unknown constant. And then I need another one because I need to count up like here in my powers. So I need 4x plus 1 squared, like that. And finally, we're on to this last factor, the x. So it's distinct, it's not repeated, and it gets an unknown constant in its numerator. Okay? Obviously, this would be a ridiculous amount of work to determine all the coefficients here by hand for this guy right here. This can be done very fast using matrices and linear algebra to do that sort of elimination computation, solving for a bunch of unknowns in a system of linear equations. But I'm not going to ask you to, obviously, I'm not going to ask you to find this many coefficients. However, this type of exercise to write out the form of a partial fraction decomposition, you can bet on. Okay, you'll definitely see that in questions. Okay, so let's do one more example right here. Let's write out the form of the partial fraction decomposition for this guy. So I'm just going to go through this one quickly because we've already talked about everything up here. The only thing that I might point out right here is that remember to make sure that it's a proper fraction first. So remember to check that the degree of the numerator is less than the degree of the denominator. And I don't know why I'm abbreviating degree. I'm not saving that much writing. Anyway, degree of numerator, degree of denominator. Degree up here is 8. And in the denominator, we have degree 2, which is squared. So that would be a degree 4 total coming from this factor here. This guy would be another 2 contributing to our degree, and another 3. So that's 4, 5, 6, 7, 8, 9. So this is actually degree 8 over degree 9. It just barely passes to do partial fraction decomposition. If this doesn't happen, remember, you need to use long division first. Okay. All right, so let's write out this quickly. So I'm going to have this irreducible quadratic x squared plus 1 for my first, and then I'll need to repeat it because it's repeated twice in my factorization as a power 2 there for another, and then I'll need this this guy right here, however, is this irreducible? Let's do a little work down here. X squared minus 4 is a difference of squares. So remember, it should factor like this. Okay, so that's actually two linear factors contained in this guy. So we would have an x plus 4 and an x minus 4. And then we have this guy linear but repeated 3 times. So we need an x squared, and an x cubed. And now let's go ahead and add the numerators. So I need an unknown line, an unknown linear for this degree 2 denominator. I need another unknown linear, because this is a quadratic. This is a degree 1, so I need an unknown constant. Linear, so I need an unknown constant. Linear, unknown constant. Same. A, B, C, D, E, F, G, H, I. Remember to just keep working your way up using letters that haven't been used before.